Yeah. So let me do a quick recap. In the last class, we looked at some basic, or we recollected some basic notions in calculus. We started with convergence, continuity, etc. Right. So first of all, we saw what do you mean by continuity of a function. In fact, it's very analogous to the continuity of a function that maps from R to R, right? So you say that a function is continuous at a point. You take any sequence that converges to that point, the function value should also converge to the function value at that point, right? That's all. That's the definition of continuity of a function. In fact, it's continuity at x, right? When do you say that the function is continuous? It should be true for all x in the domain of the function, right? That's all. And we saw what do you mean by derivative. So the analogous thing here is what is known as the gradient. Okay. So then we looked at the analogous to second order derivative. We have what is known as the Hessian, right? It's a matrix which is n cross n matrix. And then we also looked at what is known as the remainder form of Taylor series, which is quite useful tool to know. In fact, the interesting thing about this is it gives you an exact expression or exact equation for the function f of x. In terms of course, the first and second order quantities are quite clear. You can compute it. But the second order quantity is something that you don't know how to compute. But if I know that if I can somehow control the second order quantity, then I can control the function. That's what it says. Then we looked at a similar notion for a function mapping from Rn to R. Then we looked at a few consequences of this. If Hessian is positive semi-definite, what happens, and so on. And finally, we looked at a general optimization problem, how it looks like. And then we looked at the constraint set, and we started studying the constraint set, right? So we looked at a specific form of constraint set, which is called a convex set, right? In fact, this is any set. We say that a set is convex if you take any 2 points, draw a line between them, all the points on the line should belong to the set. Okay, so this is the formal definition of a convex set. And then we saw that a ball, Euclidean ball, or any ball in n dimension is in fact a convex set, right? And then yeah, so we also looked at the set of all positive definite matrices, symmetric matrices. It forms what is known as it's a convex set. More than that, it forms what is known as a cone, right? So we also saw what is a cone. And then finally we looked at a particular optimization problem, and we realized that the constraint here can be thought of as a cone which is intersected by a circle in 2 dimensions and a sphere in general, right? So let's continue. So now we have the notion of so 2 things, right? So we looked at what is known as a convex set, and we also saw what is a cone, right? Obviously, so now the question is, why do we need to study these things, right? So let's look at some intuition. It may not be that clear in the context of optimization, but at least it will give you some idea of why we need to study these sets. So typically, we consider a function which is like this, right? So in fact, in 2 dimension or in 3 dimension, it will be like this, right? These functions are called what is called convex functions. We'll see what that means. And you want to minimize this function by picking points in a set called convex set. So convex set looks like this, okay? In 3 dimension, it will be like this, right? Think of it as a ball, right? Stretched ball or whatever. And you want to pick points from this ball such that you reach the minima, right? Now what I can do is I can pour water into this function. So what do I get? Look at a bucket, right? So a bucket is basically a convex function, and you pour water into it. What do you get? You get a bucket full of water, and it's a set, right? Think of even a point here. I can think of it as a point belonging to this set. This set will be convex. Okay, you take a convex function, pour water into it, you get a body which is a convex body, right? And you have a convex body here also, right? All that I have to do is find this point, right? So somewhere here. Well, it essentially boils down to finding some sort of a distance between the two convex bodies, right? Optimization problem with a constraint turns out to be that. So that's why it's important to study convex sets before studying convex functions. Anyway, so this is something, it has got something to do with Lagrangian dual, which we will study later on. But we will start with convex sets. So before studying more about the convex functions, etc., so we will see how to make certain sets which are not convex into a convex set. So let's look at this kind of a set. Okay, so this is some set. So how is this convex? No. Why? You take any 2 points here, join a line. Most of the points don't belong to the set, right? Therefore, it's not a convex set. So how do you convexify it? Whatever convexification means. I want to turn this into a convex set. So how do you convert this into a convex set? What do you do? How do you convert this into a convex set? All that you have to do is maybe, take this line here, connect this, and take all the points here and push that into the set, right? This particular set, right, this whole thing, right, will be your, I'm sorry, this whole thing included, right? This whole thing will be a convex body, right? So how do you mathematically define this? Let's look at an example. Suppose I give you 3 points. Definitely, my set consists of 3 points. Obviously, it's not convex, right? How do you convert this into a convex set? Well, remember, you take any 2 points, join the line, all the points should be there. Of course, I'll join the line here. So that means all the points on this line should also be there in the set. So I have to push all those points. Similarly here, I have to push all those points. Similarly here, right? So that means all the points on the surface of this triangle should belong to the set. But what about this point here? Huh? See, this point belongs to the set, this point belongs to the set, also all the points in between should belong to the set. So this point should also belong to the set. What about this point? Same argument, right? So this point belongs to the set, this point belongs to the set, so all the points belong. So in other words, this whole region, triangle, is a convexification of 3 points, right? It's called convex hull. Just a name, you should remember this name. It's called convex hull. So how did we get the convex hull of these points? By taking convex combinations of all the 3 points. So there is a new terminology called convex combination. So what is a convex combination? We did lambda x plus 1 minus lambda y, right? That's a convex combination of 2 points xy. Suppose I give you 3 points. What do you mean by convex combination? So let's look at that. Okay. So lambda x plus 1 minus lambda y. This is a convex combination of 2 points x and y. What can you say about lambda? It's a non-negative number. I mean, it's between 0 and 1, right? So this is 0 and 1. This is also between 0 and 1. And when you add these two, right, lambda plus 1 minus lambda, you get 1. Right? Let's generalize that. So how do we generalize this? So let's do the following. Okay, so let's write this as a definition. It's clear. Given x1, you give me n points. Okay, instead of 2 points, you give n points in some Rn. Well, let me use k points in Rn. Okay, you are given k points in Rn. The convex combination is defined as how do you define convex combination? For 2 points is lambda and 1 minus lambda. So for n points, what should I do? Huh? Okay, what about 3 points? Suppose I give you x, y, z. So what should I do? I should multiply each one of them by some numbers and add them, right? That's a combination, linear combination. If I were to, what about convex combination? So how do you make the convex combination of these points? You should ensure certain properties. So first of all, when you took 2 points, the coefficients added up to 1.